Imagine navigating an active combat zone without knowing exactly where you are. You're under fire, the terrain is obscured by smoke, and you have no digital reference to guide your next move. For most of military history, survival in this environment meant interpreting the physical world through a handful of analog instruments. Tactical planning relied on static documents. Commanders sketched troop movements onto paper maps by hand, creating plans that were unable to update once the first shots were fired. Direction was determined by a needle tracking the Earth's magnetic pull, but these compasses were frequently compromised by local mineral deposits, harsh weather, or nearby heavy equipment. This reliance on manual tools meant that losing one's way or misinterpreting a landmark was often as lethal as the opposing force. Early radio navigation systems were the first attempt to bridge this gap. Ground stations broadcasted localized signals to help ships and aircraft calculate their position, but their range was short and they often failed in heavy storms. These systems were far from intuitive. Instead of a map display, operators managed dense numeric keypads and analog dials, calculating positions through manual inputs while under the intense pressure of a mission. The electronics were so limited that pilots in advanced cockpits still strapped paper maps to their instrument panels to verify their location. Without a common digital grid, coordinating massive operations across multiple theaters required immense administrative overhead and high-stakes guesswork. Resolving these limits required moving the military's navigational infrastructure off the ground and into the vacuum of space. The Global Positioning System relies on a constellation of satellites in constant orbit. By receiving overlapping signals from at least 3 of these satellites, a receiver on the ground can triangulate its exact position on the Earth's surface. Because the data updates continuously, this allows for the real-time tracking of movement, removing the guesswork from battlefield navigation. Shrinking this technology allowed the same accuracy once reserved for large ships to be carried by an individual soldier in the palm of their hand. That same network allows enormous naval vessels to navigate the open ocean with total precision. Every unit, from a single squad to an entire carrier strike group, now operates with absolute certainty of their position. Every GPS satellite also functions as a globally synchronized clock, providing a timing reference that is often more critical to military hardware than the maps themselves. Historically, keeping different units on the same schedule meant manually calibrating master clocks and ensuring every soldier's watch was synchronized. Atomic clocks on the satellites beam down precise timestamps, required to synchronize frequency hopping for secure military communication. This shared clock allows units thousands of miles apart to execute simultaneous strikes with microsecond precision without needing to speak over the radio. Positioning tells a unit where it is. Timing is the infrastructure that allows modern, fast-paced operations to function in the first place. Because GPS solved the problem of navigation so effectively, it became a single point of failure for the modern military. The satellites are thousands of miles away, which makes the signals reaching Earth incredibly faint. This makes the system susceptible to jamming. An adversary can flood a local area with loud electronic noise, drowning out the satellite signal and leaving receivers useless. This specialized hardware is designed specifically to hunt and disrupt these signals, turning a high-tech battlefield back into a blind one. In the middle of a fight, if the signal is jammed, the tactical interface and the absolute awareness it provides simply dies. GPS defined the precision of modern warfare, but defending that fragile signal while relearning analog backups will determine who survives the conflicts of the future.